This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So just a few reminders. Next week you will have a head tutor present various problems. All lectures will be tutorial style. I will finish with all lectures this week. So we have this and 2 more lectures. On Thursday, during the tutorial time, I would talk about the exam. So it would be a very short thing, just sort of give you some idea about what the exam is like, and you have a number of examples already on LMS. So that's pretty much it, and then I will see you at the exam. So the next week I'm away in Europe, but consultations will be organized during the SWOT week, because I will have maybe even a couple of hours of consultations in SWOT week, and also in the week preceding the exam. Your exam would be, I believe, Friday, first week of exam period. So very early on. But next week there won't be any consultations. Okay, just so you know. All right, so we need to cover 3 more things: lag compensation, lead lag compensation. That will be tomorrow, and in the last lecture on Thursday, I will present some robustness analysis. So you can see how frequency domain tools can be used for analyzing robustness of feedback systems. And with that, we will complete all the lecture material. All right, so here's the outline of the lecture. First, we will overview a few things, because we've been talking about frequency domain for a few lectures already. So I will present just a short overview. And then also we will go back to lag compensators, their transfer function, and body diagrams, just so you remember what is the Lego block we are using in this lecture. And then I will go through steps in an example of lag compensation design. And this is roughly what you would need to follow whenever you do lag compensator design. Ogata and Franklin and Powell have a range of different examples, so I encourage you to study those. All right, and then we will wrap up with conclusions. So we saw already in the last lecture an example of lead compensation. So we saw that we would use lead compensator when we want to increase a phase margin. And typically we would provide the lead from the compensator in the region of uncompensated crossover frequency. That was the main design idea that we saw in the last lecture, and we would like to do that without affecting too much DC gain. Why DC gain is important? Because of the steady state errors. So we don't want to screw up steady state errors, but we want to improve the phase margin. We saw that phase margin is related to overshoots, for instance, right? So a lag compensator is used in a different way. So we will typically use it to increase DC gain while not affecting phase margin. So you sort of don't want to screw up things too much in terms of phase, but you want to improve steady state errors, right? It is sometimes possible to use lag to improve phase margin, and actually in this lecture we will see how this is done. This is done by moving the crossover frequency to the left, reducing the crossover frequency for the compensated system, and then when you move the crossover frequency to the region where plant has an excess of phase, you can in this way increase the phase margin. You can find a range of other subtle sort of applications of these compensators. I recommend Ogata because it usually has, after each chapter, a range of solved examples and then a range of unsolved questions. So it's a very good book for drill, right, to exercise. So just to remind you, in lead compensation, we were providing, so the brown is the uncompensated plant body diagrams, and red is basically the compensated plot. So what we typically do, we provide an amount of lead in the region of the crossover frequency. Note that because of the lead gain characteristics, typically you would also move the crossover frequency. You will increase the crossover frequency for the compensated plot, and hence you would be reading out the phase margin at the new crossover, but still, if you do the design properly, you will still have enough lead, so you can improve phase margin by this design. Know that most plants are low-pass filters, and you typically have excess of phase at low frequencies, and this does allow you to use lag compensators to increase the phase margin. So by moving the crossover to the left and then exploiting the plant's excess of phase at lower frequencies. In general, lag by itself is bad. It's like a delay in your system. Lag is really similar to delay, and delay is bad. So lag is typically bad, but if you use it skillfully, you can actually use it to your advantage. And you would typically try to not, screw up the phase margin by using the lag, or potentially increase it if you use the technique just described just above. All right, so this is one way you can use lag. So one is the basic effect of lag is to basically design lag so that all the lag effects are at very low frequencies which are far away from the crossover frequency, so that the lag phase would not negatively affect the phase margin for the compensated system. And then what we are gaining by doing this, well, the gain at low frequencies can be increased without affecting too much the phase margin and the crossover frequency. So this is the basic application of lag. We won't do that in today's lecture. We will use lag in a different way to achieve something else because of the type of example that we are given. But this is the basic sort of way in which you use lag compensation. So how would you do the compensation? Well, you would choose corner frequencies of the lag compensator to be small. So basically, all of this stuff is happening at very low frequencies. At those frequencies, the plant has excess of phase. So although we reduce the phase here, it won't have any detrimental effect on the stability or performance. But then we did increase the steady state gain, the DC gain at low frequencies, and this will generally improve steady state errors. It would reduce the amount of steady state error that you have with this compensator. So this is the basic use of lag. Here's another use of lag where you now don't try to play with the gain at low frequencies, but rather the main goal is to move the crossover to the left. And this potentially can be used to increase the phase margin. So you still put the corner frequencies of the compensator at very low frequencies. The gain of the compensator is just not going to change. The way you design it, it won't change the compensated gain. So the gain stays the same at low frequencies, but then you move the crossover to the left, and note that the plants typically will have more phase at lower frequencies. And in this way, you indirectly improve the phase margin by moving the crossover from uncompensated to compensated, to the region where there is more phase excess of phase by the Planck. What is a disadvantage of this technique? We talked about this last lecture. So moving crossover frequency to be smaller, how does that affect the response, step response, let's say? Sorry? I didn't hear you. Bandwidth, yes. So the bandwidth would be reduced. That's right. What else? Rise time would be increased. That's right. So you will have a more sluggish system. So higher crossover frequency would mean that your system is faster to respond. In some systems, this is not a bad thing, like if you have larger rise time, but in some systems it is. It depends on your application. So potentially, moving the crossover in this way might cause other issues, right? Like a sluggish response. All right, so in this lecture, we would actually use this method to increase phase margin using a lag compensator. So, you know, it's sort of counterintuitive from the word lag and from the just phase plot for the lag compensator. It's sort of going to subtract phase. No matter what you do, it would always subtract phase. But since it can also move the crossover frequency, you can actually increase the phase margin. It's sort of counterintuitive. And we will do design of exactly this sort of compensator in today's lecture. By the way, if you go to Ogata, you would see a lot of examples also of this use of a lag compensator that increases the DC gain, so the gain at low frequencies, and that improves steady state errors. So please work through some of those examples as well. All right, so before we start the design, it's useful to remind ourselves what a lag compensator looks like. So the transfer function for the lag is given here, where this tau z and tau p are positive, and tau p is larger than tau z. This would mean that the pole is closer to the origin than the zero. Note that both pole and zero are real, because pole is minus 1 over tau p, and 0 is minus 1 over tau z. Since tau p is larger, then 1 over tau p would be closer to the origin, right? So what are the parameters you can play with? They are tau z, tau p, and k. So the way this compensator transfer function is given, the DC gain, or C at 0, is just k. So just by playing with k, you are playing with the DC gain of the compensator. And then tau z and tau p do affect the corner frequencies in your magnitude plot, right? So here is the body diagram for this compensator. So this was all given for k equal to 1. So when k is equal to 1, you start from basically 0, then you will go to some gain at infinity. The value of this gain at infinity is given by this formula, right? So as S or j omega, I mean, as omega goes to infinity, this is the gain you get. And that's exactly the value of this gain, right? So that's what happens when omega goes to infinity. So note here that you have this sort of lag. This starts from 0, and then you get negative, phase or lag. And this maximum amount of lag occurs at this frequency, 1 over square root of tau z, tau p. So by playing with these corner frequencies, so what I call corner frequencies, they are this 1 over tau p and 1 over tau z. They are the corner frequencies. You can play with these, and that would affect, the shape of both magnitude and phase. So by stretching this, by having larger sort of gap between these corner frequencies, you will get more lag. Why is this sort of important? Well, this sort of change in magnitude can be used in two different ways, either to move the crossover frequency to the left, or to keep the crossover frequency pretty much the same while increasing the DC gain. So there are two possible uses, and these are the examples I presented earlier. So in some cases, well, what is the goal? You want to find tau z, tau p, and k so that your closed loop system satisfies certain performance specifications. That's the goal of any design, lag design. Sometimes we also can use another parameterization. So this is a parameterization consistent with Franklin's book. So you parameterize your compensator in this way. So it's alpha, you have this t and alpha t, where alpha would be greater than 1. We will use this parameterization in this lecture. It's just sometimes simpler to work with. But look, there is no need to use one over the other. I mean, there's no preference, right? You can, do design using either of the parameterizations. This is just for convenience. All right, so typically in all lag designs, lag compensator designs, you will choose both corner frequencies to be much lower than the crossover frequency. So what does this mean? So what are the corner frequencies? They are these, So they are these two frequencies. This is where the asymptotes sort of break. And these frequencies here are chosen in such a way that they are to the left of the crossover frequency. So when you look at your uncompensated plot, this would be the crossover frequency for the uncompensated plot. Then the corner frequencies for the compensator would be typically chosen here. Now, what you can also play with is gain, right? So you can either have gain larger than 1 or gain equal to 1. So if the gain is equal to 1, you will exactly get this picture for the compensator. If the gain for the compensator is equal to 1, you will get this sort of picture. How do you see that? Well, the magnitude plot, when k is 1, then the logarithm of 1 is 0. So in body diagrams, magnitude will be 0. So adding 0 to the uncompensated plot. So nothing will change for the low frequencies magnitude plot. And then these guys are chosen in low frequency range, and you will get exactly this situation. Now, if you, on the other hand, use k that is larger than 1, then that would shift things, right? Shift the magnitude plot up. Phase stays the same. So if you imagine that you've picked the k so that this line aligns with 0, right? So you just shifted it up so that this line is now, for high frequencies, you are not changing the gain. If you do that, then you can get this sort of situation. So what this does is, at high frequencies, there is no change in magnitude, but at low frequencies, you can increase the magnitude by increasing the gain of the compensator. So in this case, you can get this sort of situation. So still, corner frequencies of the compensator have to be placed far away from the crossover frequency so that they do not screw up the phase margin around crossover. So they are the two basic uses of lag compensation or compensators. All right, so typically also the gain of the compensator is chosen larger than 1 so that we ensure appropriate DC gain for better or smaller steady state error. All right, so now we can go through lag compensator steps. So slow me down if this goes too fast for you. We will actually consider the same example as what we did in the last lecture. So the idea is to have slightly different set of specifications, but in this case we would again require increased phase margin. But this time we will achieve that with lag compensator rather than lead. So in this case, the control signal is your input to the plant transfer function, and the temperature in the room is the output. of the transfer function. So the nominal transfer function is given here. We saw it in the last lecture. It has 3 stable poles, and in this case, we will assume we can play with the gain in the plant. How you can achieve that? Well, in different ways. You can sort of enhance the control signal just with a sort of amplifier, basically. So you can get this model from regularization of nonlinear model around desired operating point. In this case, as I said, input is the control input or the actuator sort of input, and output is the room temperature. So what are the specifications? Well, we want to get still steady state error to step inputs smaller than 0.1. If you remember, this was the I think this was the requirement in the last lecture. And then we want to achieve phase margin larger than 40 degrees. In the last lecture, I think we wanted just 25 or something like that, right? So in this case, although we are using lag, we require more phase margin than what we required in the last lecture. So after compensation. So how do we figure out, well, steady state error condition? Well, we want to basically get the Kp constant to be 9, because this is the formula that we presented in the last lecture. We don't need to repeat it. We presented all the steps. But what is Kp? It's basically the position constant for the open loop gain, right? So you just let, S times open loop transfer function limit as S goes to 0, and that's your Kp constant. So we want for the compensated system to have Kp equal to 9 to achieve steady state error requirement, and then phase margin is what we need to now play with to achieve with lag compensator. So the first thing is to plot Bode diagrams for the plant transfer function that satisfies this steady state error requirements without compensation, so just K. So since I think there's S missing here, sorry. So proportional constant would be equal S times GS, that's K, and that what's required is 9 to achieve the steady state error. So Kp equal 9 would mean that K should be 9, right? So this is the first step, and we need to plot that. So this was a similar step. So this is basically Bode diagrams for the plant transfer function when we take K equal to 9. Why we took K equal to 9? Because we will satisfy steady state error 0.1 to unit step inputs. That's how we chose K. And that's what's plotted here. Step 2 is, now this is an interesting thing. So we will now further play with gain K. So there is one K that we calculated in the previous step, but now we want to again adjust K to achieve something else. So we are now saying G0 is now 9 divided by all of that, right? So that was what we plotted in the previous slide. But now we are saying here is another K, and we want to pick this K so that we choose K so that we satisfy phase margin requirements without any compensation. So we just want to see how much gain would we need if we just played with gain. How much gain would we need to achieve the required phase margin? What does this mean? Well, if you go to the previous plot, note if I now play with gain, if I reduce gain, so let's say I'll multiply this with just gain that is smaller than 1. This will shift down. As this shift down, crossover frequency would move. And what I'm saying is, let me pick where what is the required crossover frequency where I would get, let's say, 40-degree phase margin, and then I calculate the gain required to achieve this required phase margin. So I'm still sort of playing with the gain. I'm not touching design of phase for the pole and 0 for the compensator. So this is what you get. So the magnitude. So how do we do this? So we basically look at the spot the frequency at which we get 40 degrees of phase margin. This would be our required new crossover frequency. And then we look at the amount of gain, at that frequency. Well, we need to sort of have the opposite of that gain to basically shift down the magnitude characteristic so that the gain characteristic passes through that point. When you do this, you can see that to get the required phase margin of 40 degrees, you would need that amount of red gain, and it should be sort of negative. So it has to bring down the plot. If the plot was below, right, the 0, we would need to shift it up, right? So in this case, in this example, we need to shift the plot down by the amount of red gain that's given here. All right. From figure, we can see that k equals 3 satisfies the required phase margin in this example. All right. So now we need to plot the body plot of the system G0 where k was determined in step 2. So, and then we evaluate the DC gain of this system. So we basically need to redraw the whole thing. So we already decided we need to have k's equal to 3, and we replot everything. So obviously this was what we were doing was like a rough sort of estimate. We said, okay, at this frequency roughly we will need this much gain. Everything is approximate. We are not working with exact numbers. That's why when you apply gain k equal 3, then you get something that's slightly different from what we set out to achieve. But we are, for the compensated plot with gain equal 3, we get that the phase margin is actually 53 degrees. This is much better than 40 degrees that we are asked to achieve, so we are good. We stop there. We are happy with this step, right? Lots of these things, by the way, every example that you will find has infinitely many correct solutions. Yeah, so don't worry if you don't get the same corner frequencies, if you don't have the same gain. As long as you achieve the specifications that are given to you, you are fine. And that can be achieved with infinitely many different compensators, right? So don't worry about having exactly the same numbers for, the transfer function for the compensator. Right? So as long as you satisfy the specs, that's fine. And this just illustrates, this point. So rather than achieving exactly 40 degrees, which is what we were asked, here we said, okay, 53, this is fine. It's more than what we need, it's fine. Okay. So then what we are doing is we set the DC gain of the compensator to achieve desired DC gain for the compensated system. So what we are doing now, we are saying we will pick the gain to be. By the way, you need to remind yourself of what the compensator transfer function looks like. I just want to remind you. So the parameterization that we are using, here is given by this formula. So what is the DC gain of the compensator? It's alpha. What is C at 0, right? Well, that's alpha, right? Because we have this, so when you set this S to 0, then you have 1 divided by 1 times alpha. So that's why alpha is the gain, the compensator gain. So we will set the gain of the compensator to basically achieve the shift that we were talking about in the example. So basically the required amount that of the gain that DC compensator needs to provide is Kp over K, which is again, K comes from step 3 and Kp was determined before. So what we get is basically that alpha should be 9. 9 is the amount of gain that ticked off our steady state error requirements, and this 3 was the amount of gain that we required to shift down the plot to get a new crossover frequency where we have enough phase. So we divide the two and we get alpha equal to 3. So now we would know that compensator transfer function will be 3 times. We have here Ts plus 1, 3Ts plus 1. So this is basically the general parameterization where we set alpha equal to 3. And the question is, well, what should T be, right? How do we pick T now? So the last step is really to determine what T is. So we will choose the corner frequency for the 0 of the compensator to be about 1 decade below the new crossover frequency that results from step 3. So we will say 1 over T, that's the corner frequency for the 0, by the way. So the 0 here is minus 1 over T. The corner frequency due to 0 is just 1 over T, right? So we will choose this corner frequency to be about 0.1, so like 10 times smaller than the crossover frequency that we determined in this step. So the new crossover frequency here is 1.87 radians per second. So in other words, T should be 10 divided by omega C. Sorry, the new crossover, let me see where the new crossover, why is it, as I say, blah, blah, blah. I don't know, yeah, the crossover frequency, phase margin, of course. So phase margin happens at 0.92. That's the crossover frequency, right? Where we read out the phase margin. So when we substitute all of this, we get roughly, again, you see here, it's 10 divided by 0.892. Well, we say roughly that's 11. Again, you don't have to work with exact numbers. Just if it's the crossover frequency is much lower than the corner frequency is much lower than the crossover, that's fine. And then we calculate the other corner frequency from these steps to get the compensator that looks like this. So we substitute all the numbers. This is the compensator we got. Now, obviously, all these steps now need to be this compensator needs to be verified. We need to now plot the true body plot for the compensated system to check if what we set out to achieve was achieved. Why we may not achieve these things? Well, we are adding. So all the designs do, like they concentrate on magnitude or on phase plot separately. But whatever you do would affect both magnitude and phase. And because of that, we need to check, right, what we really got in the end. So here is the body diagram for the compensator and for the plant. So by the way, the blue plot is the plot from step 3 for the plant, and the red plot is the compensator plot. So as I told you, and I emphasize this again, you need to be able to add two or more body plots. If you are given, for instance, plant and compensator plots, you should be able to add them in an exam situation. I might give you several plots. I might give you, let's say, plant, actuator, sensor plot, and then compensator. So you have to add all of them, right? But 2 plots, that's a no-brainer. Anyone should be able to do this. So if you can't do this, you will probably fail the subject. So this is the, no, if you can't do this, because this would be the simplest question, right? If you can't do this, you will probably fail the subject. So this is not hard, really. So how do we find where the new crossover frequency will be? So when we look at these 2 plots now, so we want to see what is the crossover frequency for the compensated plot. So where do we look for crossover frequency? In the magnitude. we look at the magnitude, where the crossover frequency is. The magnitude of the added plots should be equal to 0. So we need to look for the frequency at which the two magnitude plots are the same magnitude but opposite sign, because when we add them at that frequency you will get 0. So you are looking at, here, so note, you have blue is going down, blue would eventually become negative, but the red thing would stay positive. So you are looking for the frequency somewhere here where blue would be negative, but the same magnitude as the red positive. Because when you add them at that frequency, you will get 0. And it is at that frequency that then, so first you pick that frequency from there, and then at that frequency you need to add these two plots, right? Note that the way we designed corner frequencies for the compensator, they are much lower than the crossover for the blue. Crossover for the blue was roughly here. So they're much lower, so note, because of that, the amount of lag at the new crossover would be very small. So we would be really affecting very little the phase margin, because we designed the compensator well. The corner frequencies are far, so the lag is not affecting us too much around the crossover. So anyway, going back to what we set out to achieve. So we are looking for a frequency at which red and blue magnitude plots are opposite sign but the same magnitude. So it would be roughly somewhere here, right? And then at that frequency we need to add the phase plots to get the amount of phase margin, right? So that's how you would do it without really having to draw the added plots. You can directly use it as it is here to basically answer the question, what's the phase margin for the compensated system. Are there any questions regarding this? I can see lots of you are sort of laughing, and then you are sort of confused, and look, my goal is to teach you something, or you should be able to learn something. If you didn't learn this, then you really can't pass the subject. Yep. So the first thing was to design, to find the amount of gain which would give us the right steady state error, right? So by the way, maybe I should draw this on the board. Let's see whether this would be. I avoid using the board because lots of people, as you can see, are not attending the lectures, so I want them to benefit. So when you listen to me, at home, so you should appreciate that. But this is a situation where I can't avoid using the board. So what we are doing here is, all right, we have. Can you see? Can everyone see this? Can everyone see this? So this was the, let's say, uncompensated plant. Well, actually, in this case, it's tricky because we had that the plant had this gain S and then K, and then there was 2S plus 1, there was S plus 1, and I think there was 0.5 S plus 1, something like that, right? So first we chose K, right, so that we satisfy the steady state error characteristics. So we got around, I will not be writing everything in decibels, I will be writing it with just normal numbers. So we saw that 9 was what we were asked to provide to satisfy steady state error. And then we got gain characteristic that looked like this, right? So then, obviously, this is not the full story. There was some phase characteristic as well, right? And that was going to cross minus 180 degrees at some point because we had 3 poles. Each of the poles would contribute minus 90 degrees. So eventually the phase would cross, minus 180 degrees. Then we were saying, all right, what I want to do is I want to design a compensator that would distort the magnitude plot in this way. Something like that. I want it, so I don't want to mess with this guy here, right? I want to, the DC gain, but I would put corner frequencies of the compensator much lower than the crossover here, so that I affect the crossover frequency, but I don't affect the DC gain. So how would I achieve this? First, I'm saying, let me shift down without the compensator. So this thing here would be due to the compensator. But first I'm saying, forget about using compensator. Let me see how much I need to shift this down so that I achieve the required, well, this is not drawn properly. So let's say that this is your maybe minus 180 degrees. So you have some phase margin here, required phase margin. So what I'm first asking is, so first I designed K to tick off steady state errors. Then I'm saying, let me now shift down the K, shift down, so that would affect crossover. And I want to pick new crossover just by shifting gain, so that I get the required phase margin here. That was the third step. You asked me, how did we do that? Now, why did we do that? Well, because when I shifted down the gain here, compensator itself would provide some gain. So I would have actually, in the end, something like this, and I picked the 3, so compensator gain, so that it brings me back to this point. And so the whole idea is to get the desired DC gain, get the desired crossover, right? But, you know, by doing it with lag, you can then choose the gain of the compensator and corner frequencies in the low frequency range, so that, well, the compensator would sort of have some lag, but it will have it here. But it will have moved the crossover here where Plum had more phase margin itself. So that's the philosophy behind the steps. Yep.
And that K design, that's very like in the final transfer function, that's very used.
So we could use, so is your question, is this gate the only choice, or?
Well, is that K the K design, does that still remain in the transfer function, or is that accounted for in the?
So in the end, the open loop transfer function for the compensated system would be G0 times C, right, in the end. And we are trying to figure out C, and we are always trying to design one thing at a time, right? But the problem is, as we are designing one thing at a time, we are concentrating on one of the plots, either gain or phase. We will be screwing up the other one because we are playing with gain. Well, that will affect the phase. But, and look, there is no simple or unique solution. We could have chosen the gain K or Kp to be 10 or 50. That would still satisfy the steady state error, right? But it would be harder to design a lag compensator that achieves the other requirements. Yeah.
I think that why the compensated part is still benign. I think that the low frequency part should be down. I think from the beginning and low frequency part, because the K is not 9 anymore.
Well, what we are trying to do here is we are trying to actually design the compensator gain, right? So you I mean, can do this in different ways, right? We could have said the plant gain is fixed, and then we would be trying to design compensator gain. All of the gain would be then translated to the compensator itself. In this case, the fact that we said, okay, we can have this pre-compensation, right, by picking K in the plant itself, then this K wasn't part of the control transfer function. But this is just specific to this example, right? Does this answer your question? No.
Discuss.
Can you repeat your, we have time, so.
Because I think that the 9 is the KP, right?
Yep.
The 9 is the KP, and the alpha should be 3 at this time, right?
Yeah.
Maybe I describe it because I can write the equation.
Okay. All right. Okay. All right. So finally, we need to plot everything. So here is the plot when I added the two plots. So this is now the full design. I added the plant and compensator plots, and this is the outcome. Note that in this case you have the phase margin to be, 49.4 degrees, right? And it is at a lower crossover frequency than the uncompensated system. And note that the gain is at the right spot, because in the end, after all the steps, we still, so think of these things on the whiteboard, we managed to maintain the gain required for steady state error. We moved the crossover frequency to the left. At that frequency, we had more phase margin, and the lag was added at lower frequency, where we had excess of phase. So note this dip. This dip here is due to the lag compensator. But that's so much sort of so far away from the crossover that it doesn't affect phase margin or anything. So we're still good. So that's it. This is the end of the design, and we achieved all the requirements through these steps. So by the way, last step would be iterate on this until you get the right answer. What could have happened? You could have chosen crossover frequencies of the compensator too close to the uncompensated or desired crossover, and then this amount of lag could have affected more what's happening around this frequency. So if that happened, you may not have obtained what you wanted to obtain. And if that happens, you need to repeat. And how would you repeat? You would then push the the corner frequencies of the compensator further to the left. You will make them smaller. So that would be the iteration. The gain you typically don't need to iterate on, but the corner frequencies you need to move more to the left. So that's the iteration step. So this is only one way for doing compensation. There are other ways, right? So obviously you if you follow different books, they will have slightly different steps. And different books would even use different parameterization of compensators, and different parameterizations would lead to different rules, right? When you understand really all the steps that we went through in these two examples, feel free to come up with your own. I mean, you can say, well, this seems to be like an easier way, shortcut or whatever. Don't worry about the exact mathematical formulas, as long as in the end you obtain what we asked you to obtain. So if you satisfy the specs, you are fine. There is lots of freedom in the way. So for instance, I picked the corner frequency of the zero in this example to be 10 times smaller than the new crossover. You could have chosen 15 times, 20 times, right? These things are not set in stone, right? And then, I mean, once you really master these, you will understand there are really many different ways in which you can achieve it, okay? So what we did today, we presented these typical steps in compensator design. So we worked out this example. We saw all these different steps. We saw that lag compensation can be used to either improve steady state error by adding the extra DC gain. We did not present this example. We just talked about it in the lectures. But we also saw that we can increase the phase margin by placing the corner frequencies for the compensator as much lower than the crossover. So that's all. Any questions? Yep.
Yeah, just one. It seems like the further left you place the corner frequencies, sort of less it affects the cutoff frequency. Is there any disadvantage just pushing the corner frequencies absurdly fast on left, which would always meet the requirements and never mess with the conservative frequency?
Good question. I mean, that depends on the case you are considering, right? So typically they would be small anyway, but it would really depend on the situation at hand. In all these designs, I typically give you a set of specs, and then I say, okay, to achieve this set of specs, you have to follow these steps. But every time we are not considering a range of other things that might be important. So in every example you do like this, we are now concentrating on steps to achieve something. But in the end, you need to check what your sensitivities are doing. And all of these things you are asking that would have effect on all the sensitivities. So in the end of the day, you have to plot all your sensitivity, transfer functions, Bode diagrams, and see what you get. And then if there are any peaks, any sort of undesirable behaviors, you may say, well, in the beginning, I didn't want this to be part of the specs. But now I can see that this is important. So you go back and you revise your specs, right? But it does affect everything, really. Okay, well, thank you very much. I'll see you tomorrow.
When you say this
So in the last lecture, we presented a detailed formula, steps going from here to here. In the last lecture, I said that.
What about this question?
So this was just our choice. I said I want corner frequencies to be much lower than this. So I wanted to just show the corner frequency is more. That was the choice. I think the choice is 0.1 can be 0.05 or something else. But as long as you achieve what we set out to achieve, then so we have consultation. But I have to run and get something to eat. But then I have to eat 3 hours of art. I need to do that.
How about this one?
If you can walk with me.